So welcome everyone. It is my pleasure to welcome you to this other appointment of our 40U40 lecture series on combustion. And today I have the great pleasure to introduce Professor Mariano Sirignano. Mariano is an associate professor of chemical plants at Università di Napoli Federico II since December 2022. In 2011, he obtained his PhD in chemical engineering at Università di Napoli Federico II. And he also has been a visiting PhD student at the University of Utah and at the University of Sydney. So Mariano has already a number of very important accomplishments from our community. He has won the Bernard Lewis Fellowship of the Combustion Institute in 2012 and also the silver medal of the Combustion Institute in 2014. So his research activities have focused on modeling and experimental investigation of combustion-generated particles, and recently he has shifted his attention also towards the possibility to exploit the features of combustion-generated particles for novel applications. So Mariano, thank you very much again for having accepted our invitation, and I give you the floor for your lecture. Thank you.
Okay, good morning, everyone. And thank you, dear hosts, for having me here. It's a pleasure for me to deliver this seminar because I think the idea of this different look from the under 40, at least we try, it's challenging for us, and it's probably something that the whole community can benefit from. I'll start saying that when you asked me to give this seminar, I was troubled to choose the topic because there are so many hot topics that nowadays can be in some way presented to the community, and I decided to stay focused on one of the topic that intrigued me most since the beginning, and now, as you said, shifted my attention towards a different aspect of this topic. So how we can exploit what we have done so far for a different application. That's why it's called this seminar start with the word upcycling. So in some way, it's the idea of using something that we have so far looked at as a byproduct, something undesirable, and see if we can have the better of it. I have to say the first thing that we are going to talk about combustion-generated particles, but to be honest, we are going to talk about combustion-generated carbonaceous particles. There is an entire world moving around the inorganic, let's say, particle generated via flame synthesis. I'm not going to talk about it, but just it's worth mentioning. So we are trying, I'm going to pose 3 questions, and I'm trying to give at least my point of view on these 3 questions about combustion-generated nanoparticles. What are indeed carbon nanoparticles? How we can produce carbon nanoparticles, and I will try to understand, to explain what I mean with how can we produce carbon nanoparticles, and in the end, how can we exploit carbon nanoparticles, at least in a different way from what we have done so far. So basically, we start from carbon, which is a great versatile element that we have in different allotropes in nature, and of course we have also in a very smart form. We are basically built on carbon chemistry, and if we talk about the carbon allotropes, we can have a lot of very famous, let's say, material or nanomaterials. You can see a couple of Nobel Prize here: fullerenes, graphenes, carbon nanotubes, but also nanodiamonds, amorphous and glassy carbon. These are allotropes of carbon that can have very peculiar features and that have inspired the scientists all over the world to pursue the search for producing them and for using in a very smart way in a very different application. For example, graphene is famous because in Europe we had a flagship program, and we put 10 billion euro in graphene research. We have accomplished so many in understanding how graphene works, how it's going to be great for optoelectronics and for many devices. But the very question that we should ask right now is why graphene is not in our smartphone? Why is not yet in our everyday life? Since it's supposed to be the material of the future, why is not the material of the present? And when and if this is going to be actually a real thing. For example, carbon nanotube, you can see here, this is the cost that I just downloaded yesterday for carbon nanotubes. We are talking something that is still twice as pricier than platinum. And with a purity that sometimes is not even enough for what the original idea of their application is. So many of these, let's say, promise of these carbon allotropes have not been maintained so far. And the reason is there is no such a way of large production systems for these very smart materials, let's say. There are a lot of ways of producing them, even from waste materials, which is kind of a dream. You know, you have a waste material, you apply some process, and you obtain very smart nanocarbon that you can use somewhere else. The problem is that the process applied so far for these for obtain nanocarbon from all these wastes, it's something that it requires a lot of energy. It's a complicated process. Sometimes it's dealing with low purity, so then this nanocarbon needs to be purified. And on the other side, what we can propose to help the community to have to step up from the lab and going into large mass production of this nanocarbon, we can propose flame synthesis. We have studied the material in the carbon nanomaterial for a very long time because we thought it was a byproduct. And now we are talking about nanocarbon as a material, possibly a new material. So what is in common between these two sides of the story? What is in common is that the high knowledge that we need on soot formation and evolution to completely control the process. So the complete control of the process of nanocarbon, it's allowing us to have tailored features in terms of size, composition, and atomic organization. Is the same knowledge that has been used so far for preventing the formation of this nanocarbon in combustion processes. Okay, so the idea of turning that knowledge in something that we can exploit from a different point of view, I think is sounding and promising. And as you mentioned, I am a chemical engineer. So my approach to this problem is that we treat the flame as another maybe complex reactor in which we can define some typical parameters for reactors, such as residence time, temperature history, reactant concentration and nature, and mixing properties. I wrote some of the typical time scale that we have for our combustion reactor, and you can see that our reactor, the flame in general, the combustion chamber, can explore a very different condition. It goes from nearly room temperature to up to even more than that, even more than 2500 K. We can have the largest moiety of compound used as a fuel. We can have different type of mixing, premix diffusion. We can be helped by turbulence by having some multi-phase reactor, for example, or something like that. So if we can manage to understand how these parameters influence the production of nanocarbon, then we can control this parameter, or we can use these parameters to control the production of the exact nanocarbon that we want. Just to stress one thing, we are not really going to produce graphene. This is not the topic of this seminar. What I'm trying to show in this seminar is that we can still tune what is produced in terms of nanometric scales carbon in flame, and I think that it is already have it already has some very interesting features that can be already exploited without going into very smart material like graphene. That's the idea. So this is what is generically called soot. Even in the slide before, this word came up, and of course, everybody that has been working combustion at least heard of the soot problem at least once. So it's generically called soot, whatever it comes is in solid state from an hydrocarbon flame. But soot is a very generic it's a very generic word that contains very different things. To be honest, it's already a material. It's one of the largest sold, the most sold material in the world, and used mainly for inks and tires in the rubber industry as a reinforcement. So we are not, in my opinion, exploiting all its potential. But in combustion, are we really producing just soot? This is a word that has been on for years now, for decades, if not more. And even in the scientific community that is studying this, and is still used as a generic term for combustion-generated carbonaceous particle. If you, on the other side, is coming from a different perspective, for example, from the industry, you would maybe call it carbon black. Carbon black, it's exactly the same as soot, and it's almost undistinguishable under a microscope, for example. We can say that carbon black is probably a specific form of soot, so like a soot with a very specific feature, for example, with a very low amount of what is called organic carbon, for example. This is just to open you the perspective that the idea of possibly tailoring the size and the morphology or the aromatic content in the carbon generated in combustion generated carbon particles, it's something that it's already been done, for example, by carbon black industry. I think we can exploit our reactor even more than this. In fact, if we look into the soot, what does soot, like generic term, contains? Carbon nanoparticles generically has been looked into for a very long time. And this is a very famous picture, at least it was a very famous picture when I was starting this work 15 years ago. And it's coming from the Heidelberg roundtable in 1994. And you can see that for the first time, or one of the first time, there was a bit of consensus on the fact that polycyclic aromatic hydrocarbons were the building blocks. That was the usual sentence that you can find in many papers at that time. The building blocks for the particle. There was a lot of study in the progress for the large soot particles, their optical properties, the size, the first microscopic studies, etc. But we are talking about the very end of this figure. And there was a generic consensus on the main oxidation, and also the formation of pH was starting to be precisely studied by ACA mechanism and resonantly free stabilized radicals. But still, at that time, there was this what it was called the dark region by van der Waal, and in the between there was the inception region. So how we move from a gas phase to a solid state phase. So in the year in the beginning of 90s, practically simultaneously, Dobbins and D'Alessio were finding these particles in that region with properties that were significantly different from everything that they have seen so far. So from that moment, every scientist that has been encountered these particles in this dark region have called in a different way. We start with Soot precursors, nanoparticles, even white Soot nuclei, precursor nanoparticles, non-organic carbon, but generically also Soot. So just combustion-generated particles, to be honest. In the years, we found it almost everywhere. We found it at the exit of engines, but also when we use natural gas on the cook stove or on the heater. So these nanoparticles, and here I'm using this word to let you understand, with very small size and different properties, and in a minute I'm going to show you what I mean for this. They are everywhere, basically. So the things started to be very interesting at that point. And the reason that why everybody has a different definition is because the only thing that everybody was agreed on is the fact that these particles were freshly nucleated, which means like they were the very first things in the condensed phase state. Okay, I wouldn't rather call solid, because there is also like the idea that they were not exactly solid particles, but for sure they were in a condensed state phase. So they were definitely the first nucleated particles. And so, which means that different particles definition, they comes from different particle properties that they were investigated: the size distribution, optical properties, H to C atomic ratio, and general physical chemical properties. And this led to a different inception mechanism. For example, the growth of two-dimensional pH, the physical coalescence of the stacked into the pH into stacked cluster, the coalescence of pH into cross-linked the three-dimensional structures. These were like very well depicted in the plenary of Professor Wang, and back in 2011. And since then, we have moved, and more inception mechanisms have been proposed, more precise according to new findings on the properties of the particles. But the experimental approach was so important that here I'm going to divide it in two categories: the in situ techniques that were probably the first things that we used to detect these nanoparticles, and we are talking about extinction, but also laser-induced emission, both fluorescence and incandescence. The problem is that with these in situ techniques, we don't get that much detailed chemical characterization. So we also tried to sample particles from the flame, and then we applied all the ex situ techniques that we know. Of course, the flame is going to be perturbed, but we get much more information about the optical properties, their hydrogen content, the sites, and all the rest. So the mix of these two experimental approach, gave us a very complete picture of these small nanoparticles. Still, there is a lot to understand, but there are some aspects of regarding these very small nanoparticles that can be that can be summarized. Many groups, I'm sorry if I don't cite correctly all the groups that they have been working and are still working on all these experimental procedure to get information, insights on particle generated in combustion. And you can see that at the end, I also put advanced modeling because at a certain point, the possibility of using very advanced modeling of stacking to understand nucleation has become as important as the experimental application. So what we get from all this, we get that we can definitely say that in combustion can be generated, particles are generated, have two different properties, belong to two different classes. One, it's on the right, you can see it's the old Soot, what is more close to the old definition of Soot. The first one, it's so far from the definition of the old definition of Soot that, in my opinion, it's worth to classify in a different class. According to the recent findings and the definition, what is produced, which is not Soot, probably it belongs to the category of carbon dots. Okay, nanoparticles or carbon dots that recently have gained so much attention because quantum dots has been the object of the last Nobel Prize in chemistry. So what is the difference? For example, starting from the physics state where solid is applying to Soot, for carbon dots, it's probably more correct to talk about condensed phase because it's between a liquid and a solid with viscoelastic properties. In fact, some of these nanoparticles have been seen to splash on a surface where Soot is not able to change its shape when it hits a surface. Recently, carbon dots have been seen not absorbing down to the IR, so not in the visible, not in the IR, or like very low absorbing, like below our sensitivity, where Soot is able to absorb all over the range. For these nanoparticles, like these nanoparticles that exhibit these properties usually are no larger than 10 nanometers, and in most cases below 5, where Soot goes up to 100 nanometers, with the primary particle going between 10 and 30, 50 nanometers. And then we have the possibility of having fluorescence from these carbon dots, which is very important. I'll show you why. In the UV and in the visible, with very high quantum yield, where Soot is not able to fluoresce, while instead is very known to be an easily incandescing material. A completely different H to C ratio, which means different aromaticity. In terms of carbon network, we are talking about graphitic versus amorphous. In terms of solubility, we are talking about partially soluble in water. It would be more correct to say dispersible because it's not really a solution and it's not soluble in water. It's possible to generate different surface from hydrophobic to hydrophilic. We have seen, for example, that these carbon dots at flame temperature have a very low and size-dependent coalition coefficient, whereas Soot has a unitary coalition coefficient. The problem is that these very small dots account just 90% of the total number, but as you can see here, they are completely negligible in mass, whereas all the mass is contained in the Soot that has been produced in the flame. Different range of density, and at the end, also different emissivity. All these things have been, in some way or another, found experimentally with the contribution of all the community, and I'd say basically everyone that has been working on this topic has given his brick in this wall. So, two different materials, which means which is the the conceptual modeling beyond these two different materials. We start with pH formation. We end up with large molecule formation. You can here see that these are cross-linked molecules, so you can have also large pH, probably in very low concentration, but you can also have large pH. At a certain point, we have inception. We are not 100% sure still which is the mechanism, the chemical physical mechanism for the inception, but we know that at a certain point, these large molecule behave as in condensed phase state. And then we have the particle evolution. This is something that I'd say we understood better. So the evolution of this particle, their hydrogenation, the cross-linking, internal cross-linking formation, etc. So the first, let's say the first part, it's let's say still in the gas phase, and this is in condensed phase. Here I'm reporting just few of the properties that I mentioned before. You can see that the first particles have something that it's not more as in gas phase, but they still resemble the gas phase from where they are generated. So, for example, they absorb and fluoresce in the UV, which means that the aromatic island is not that large. And here you can see also in terms of sites, we have gas phase, we have this nanostructure, carbon dots, or whatever you want to call. Then we have a primary particle, and then we end up with aggregates. I just want to show you that the fluorescence, it's something that you can see in the first part of the story, because this nanostructure maintain a molecular-like electronic transition and can fluoresce. Actually, with the higher quantum yield with respect to the gas phase, and this is due to the fact that they are in condensed phase, they are, in the end, they dots, okay, carbon dots. And then at a certain point, there is a transition towards incandescence, where the particles are not able to fluoresce anymore, and they are able to accumulate the energy. At the heating up, they are heated up, and eventually they emit a carbon black or a quasi-carbon black, black body, black body emission, or a quasi-black body emission. Here I use this conceptual modeling to point out something that for me, I think is very important. For years, I think we have been looking for the missing link between the gas phase and the particle phase, like if it were just one single specific particle that can be designed or entitled to be the missing link between the gas phase and the solid or condensed phases. And also, when we found out that there were these nanoparticles, we were looking at trying to find which is the last particle that can belong to the nanostructure or the dots, and which is the first particle that can be called Soot. I think this is an approach that is really not seeing the point. This is a continuous transition, especially when we move to the condensed phase. It's a continuous transition from the very first particle generated to the last particle, to the last aggregates. It's a continuous transition. Particles are start to able to absorb photons and re-emit photons in as fluorescence, and they grow. And at a certain point, these photons are not able to leave the particle anymore. They stay there, the particle is heated up, and then start probably to have a little bit of fluorescence and a little bit of incandescence, probably in dependence on the energy of the photon and the temperature of the flame, maybe, or something like that. So it's probably a continuous transition, which has a very specific particle on one end and a very specific particles on the other end, but not something easy to catch up in the middle. Just to show you something about fluorescence, this is what we found, and in flame, you can see here the very all the measurements is almost 20 years ago, more than 20 years ago, about the pH in a cell. and you can see that their quantum yield goes down to practically the response of the system when the temperature is increasing, not even close to the flame temperature. Okay, and we are talking naphthalene here. What we found in flame, you can see in the graph in the bottom, it's that the LIF that we measure in flame at flame temperature, so we are talking about at least 1500 K. This was measured in premixed flame, so there was no doubt about which was the temperature of the flame. We are way above 1500 K. It's longer, it's significantly longer than the gas phase pH should be. So we have very similar spectrum with a completely different quantum yield. That's a very important hint for understanding the nature of these carbon dots, because they resemble the gas phase pH, but they are longer in living, they have a longer living fluorescence, in saying that they are in fact in condensed phase. Okay, this is an example of how an experiment can suggest something related to the nature of this particle, but also just something about the mechanism of the reformation. I will leave it there for the let's say for the more base scientific part, and I would like to move to particle production, because what we can do, for example, let's look at the elemental carbon. So what is generally called soot. How we can tune the structure? How can we modify the structure? For example, we tried to use a different to collect on glass plate, very easy. With thermopholetic deposition of glass plate in a different premixed flame. Okay, what we changed was the aromatic content in the fuel. We moved from a pure ethylene, which is the paraffinic fuel for excellence for soot. We moved to benzene fuel. And you can see that the color of the flame is changing, but look at that, also the color of the glass put in the flame. You move from something which is dark black and something which is grayish or something like that. So we modified the structure of the soot, and the first visible, let's say, effect is that the soot is not more black, let's say. So the Raman spectroscopy suggests that moving from the pure ethylene, so B0, to pure benzene, B100, the sites of aromatic island significantly changed. For people who are not expert like me, for example, in Raman, the moving from 1.05 to 1.2 in terms of aromatic island, it's significant. It's saying that the soot formed with benzene is significantly more aromatic. But the same soot, we also did absorption spectroscopy to understand the optical band gap. Optical band gap increase means something moving towards semiconductor, okay? And what we see is that moving up with the benzene percentage, we move towards 0, which is typically of graphite. So basically, if we combine the two measurements, we can say that we can tune our elemental carbon, because we can have a very graphitic carbon with a optical band gap that goes from 0.8 to 0.2, or looking on the other side, we can have a very low optical band gap with a graphitic structure that goes from 1.08 to 1.22. This is where tuning structure and optoelectrical properties is by changing fuel composition is very important, because this kind of nanoparticle soot can be used in photocatalysis, but also supercapacitor, batteries, and fuel cells. So this could be a way to tune our particles in a very simple way, just changing the amount of aromatic fuel in the amount of aromatic in the fuel. And let's look at the other part, the carbon quantum dots or carbon dots. how we can produce and modify. Just to show you the carbon dots or the semiconductor quantum dots are why we want to that, because they have a high biocompatibility, photostability, low toxicity. And they have strong emission in the visible region when a light is pointed to them. So in the past, this is an old picture, but in the beginning where people were start looking into carbon dots, but you can see there are many different ways. And even from the beginning, flame synthesis was in fact something to produce at least the bulk material for carbon nanosynthesis. In this particular approach, the carbon when after treated with chemicals. What we try, this is just a general picture to show you that our particles resemble carbon dots. There are a different possibility to have dots. We have graphene quantum dots, polymer dots. Our particles is between carbon nanoparticles and carbon quantum dots, so belonging to the class of dots. But what I want to show you is that, we use the same apparatus that we used before. We collected on the plate. You can see that in this case, the glass plate was multiple inserted in the flame, and the glass is definitely black. And then we applied a very simple procedure. We wash with an organic solvent, and we use a very fine filter to filter out all the large particles. So just the carbon dots were remaining, and then we analyze it. We dispersed in the NMP, which is a very convenient solvent for this kind of particles. And you can see that after the filtration, the liquid is clear at normal condition. But when we use an UV light, you can see that the fluorescence color is completely different. Once again, just changing the aromatic composition in the fuel. So we can tune the emissivity of the carbon dots just by changing the benzene composition, the aromatic composition in the fuel. That, from the chemical engineering point of view, it means just changing the fuel, the reactant properties, okay, the reactant mixture. This is a very simple parameter to change. We kept constant as much as we can the other condition. This is the effect of the fuel in producing different carbon dots. And then in the end, I'll try to keep it short. I want to talk about what we can actually do with these carbon nanoparticles different produce. And I want to show you some recent uses that we found and very interesting. For example, we can put it in viscoelastic medium. We use surfactants. Surfactants can produce micelles. Micelles can have a very different form. You can have spherical micelles, but also you can have worm-like and entangled micelles, even with very, very low concentration in water. Okay, so we are talking about something which is like 99% water. So it's something very sustainable also from environmental point of view. Remember that carbon nanoparticles are practically not dispersible in water. When we use this micellar solution, we were able to obtain a solution of 10,000 ppm of soot with a stability, with little or no effect on rheology. So we can control the rheology of this stable dispersion with just a very little amount of surfactant. There was no effect on interfacial tension, and there was very long-term stability for this. Over months, we were able to store and preserve without losing any material from this dispersion. Which are the applications for this kind of dispersion? Well, for example, the rubber industry could use less material. They could have a better mixing, and which will turn in a different properties of the rubber that they are gonna use. We also try to do carbon particle aerogel in a very simple way. We use soot produced by a pure ethylene flame. We put in a chitosan solution, a little bit of sonication, and soot was completely well dispersed in this solution. With the freeze dyeing process, we obtained this very little sponge, black sponge, that we used for cleaning up water from dyes. Okay, indigo carbonate was completely and efficiently removed by this carbon chitosan aerogel. Okay, this is a project that there is a project founded on this for the future. We try to use this material just to show you that what we produce is something that is comparable to GO. GO stands for graphene oxides. Graphene oxide, it's basically has the same ability to clean up the water of our material. It costs probably between 100 and 1,000 times more than what we produce. So that's the idea. Sometimes using graphene oxide is fancy, but it's not necessary. We also produce thin film. We deposit it on the substrate. And also try to apply an electrical field to change the deposition of the substrate to obtain a different film deposited on our substrate. You can see that moving from 0 to -3 kilovolts, so without and with the application of a potential, so the deposition is completely changing, and not just in terms of amount, but you can see also this fractal shape particles deposited formed onto the substrate. And this is just to show you better, like with the skeletonized image, that is a completely different film deposition, not just in terms of amount, but also in terms of the structure of the film. We also performed a little bit of modeling, and we were able to follow this deposition, enhanced deposition of small particles as small as 10 nanometers when the electric field is applied. Just to show you that these films, as I told you, is super hydrophobic. You can see here we are trying here to deposit very gently a drop of water on one of these films, and you can see here that the droplet is completely super hydrophobic with the tilt angle very, very low. The problem is that this film can evolve in a very strange way because when it stays for a long time, the interaction with the droplet and film, it's very complicated. You can see that you can have a very, let's say, even a sticky surface. So we have a hydrophobic surface with the sticky effect on the particle. So there is a lot of still to understand on this kind of film. And in the end, I want to show you what we tried recently. We put carbon particles in cell. We didn't put large particles. We use carbon dots here. So we should be saying carbon dots in cell. We found out that our carbon dots are uptaken by cell, healthy cell and cancerous cell at a different rate. This was a very surprising outcome of our experiment. So it seems that the carbon dots prefer to enter in the cancerous cell at very low dose, so without being toxic for both a healthy cell or cancerous cell. What we found, and I won't go into details because most of these details are even obscure to me, let me say, is that particles, carbon dots, when they enter in the cell, even if they do not have a significant effect in terms of cell vitality, they can modify the cell. Recently, we found that they can actually enter into the nucleus, which is very peculiar for this kind of dots. So our combustion combustion generated carbon dots can enter into the nucleus. One of the first things that they could be used for is to size the nucleus pore, which is a very debate argument in biology. So we still can use the flame to tune particle feature and then use these carbon dots to explore very different aspects of the science. Summarizing, like look into the future, what we know and what we can do. We know that we can produce different carbon particles with different features. We can know that, for example, for the large particle, we can tune structural and optoelectrical properties, and we know that we can change the band gap and the fluorescence of these of the carbon dots. There are large amount of diagnostic and also modeling that we can apply to understand better which are the processes and controlling the processes to produce the exact feature of the carbon that we want. From the industry, what they have done so far, where they still produce a lot of carbon black with the old methods, top-down gas phase synthesis, furnaces, and they are just interested in yield. As the yield goes up, they save money and they are able to convert more fuel into carbon black. But carbon nanomaterials can be exploited in a different ways, as I just showed you. And to do so, people have done a lot of functionalization of this nanomaterial. The graphene oxide means that we need to add oxygen for treating then graphene in solution, and then in other condition for the semicapacitor and all this stuff. So usually this has been done as post-process after a very complicated production that, as I told you, has not led us yet to having graphene in our smartphone. So the idea is that we can use our expertise to controlling the size and the chemical composition of the particles, setting up a new design, exploring the possibility to functionalize in situ. For example, using the liquid-liquid particle interaction to spray soot or carbon black in a functionalization reactor. And I moved to what is one very recent project that we got financed, and I think that it's exciting for us, and I hope for the community in the future, to have a functionalized carbon black in the same reactor where we produce the carbon black. I thank you for your attention, and I'm open for questions. I hope I stayed on time.
Yes, absolutely. Thank you, Mariano, for this very interesting talk. Okay, it's now time for your questions from the audience. So if anyone from the audience has a question, feel free to raise your hand. We'll give you the virtual floor to ask any question. For now, we don't have questions, so I will break the ice and ask you. I have a couple of questions. So if you let me, the first question will be on this definition. It's a curiosity on the definition of carbon dots. Are they really? We can still call them carbon dots, even if the hydrogen to carbon ratio is 0.3, 0.5 of the order of unity.
Yes, look, the idea is that according to, let's say, this definition, carbon dots, not quantum dots, but carbon dots can be found in let's say, in a more graphitic structure and in a more amorphous structure. Usually when you have amorphous structure, you talk about an H2C ratio much larger than the usual Soot H2C ratio. Also for the carbon quantum dots, we are talking about an H2C ratio much higher than the usual Soot H2C ratio. Think that a pyrene molecule has an H2C ratio which is above 0.5, because we are talking about 10^16 hydrogens. And for years, we have, for decades, we have used hydrogen as the single precursor that we believed was able to stack. So the very first carbon dot imagined back 20 years ago, something like that, he had an hydrogen carbon ratio of 0.6, maybe a little bit less if you consider a larger molecule to stack, but that's the order of magnitude. And remember that, for example, from a fluorescence point of view, you don't have a fluorescence from these carbon dots that goes deep in the visible. It stays in the UV mostly, which means that most of the aromatic island has 2, 3, maybe 4 rings, not definitely 10 or more rings. So the idea that these carbon dots have this very high hydrogen to carbon ratio, it's not a problem for the definition of dots. They still exhibit the high quantum yield and other properties typical of these dots. It's a matter of definition. It's not really. It's not really important. It works. For example, they have a very high. I show you the cell result. One of the things that we found that they are still extremely fluorescing even when they are put in cells. We were not able to tell until the experiment if these carbon dots were actually able to fluoresce even after the cell internalized them. And we found out with big surprise that these carbon dots were still able to significantly fluoresce with very high quantum yield.
Okay, thank you. And my other question would be on the fact, upscaling this process, and like you mentioned about use of waste to then come up with this product, carbon products. So we can still rely on the on changing the conditions of the reactor, or we have to rely on some post processing.
In some way, in some way, the carbon black it's already produced with some waste, in the sense that most of the time the oil used in the carbon black furnaces, it's not high quality oil. It's something that it's hardly can be used for different purpose, and then it depends still again on the quality and all the process and on the market. Most of these waste material come in the form of oils or some like let's say liquefiable or dispersible material containing carbon that can be in some way elevated to nanometric sites by using flame synthesis. So that's the idea of nobilitating some of the waste material by using flame synthesis, giving them the sites of nanoscale, which means that probably we lose a little bit of energy in the process, but we, let's say, upgrade the quality of the material, of the starting material, having them at nanometric sites, which is which I think it's quite it can be quite important.
Okay. If there are no more questions, I think we can. And it doesn't seem so. I mean, it seems that there are no more questions. So I would like to thank you again, Mariano, for this interesting talk, for choosing this alternative, let's say, topic on combustion, showing us the potential of combustion for nanomaterial production, which is something, yeah, very new and trendy. So thank you again, and thank you for having accepted our invitation. And
thank you for hosting my seminar. It was a pleasure for me to share ideas with friends.
Okay. Thank you, and thank you everyone for attending this presentation and this webinar, and we'll see you at the next appointment, and have a good weekend, everyone.